Welcome to qnawire.
Given this function f of x, and the first thing to figure out the intervals where we're increasing or decreasing that we're going to have to do is find the derivative of this function. So f prime of x is equal to, using the power rule, 8x squared, or sorry, not 8, 6x squared minus 18x plus 12. And we can simplify this by taking a 6 out, so we get x squared minus 3x plus 2, and then we can factor this, so we get x minus 2, x minus 1. And now we know that we have zeros at x is equal to 2 and 1 since we factored this. And so what we're going to do is we're going to look at values of x that are less than 1, look at values of x that are between 1 and 2, and then look at values of x that are greater than 2, and we're going to see what the sign of our derivative is. So if we plug in a value that's less than 1, let's just say 0, we would get 0 minus 2 is negative, 0 minus 1 is negative, so we get a negative times a positive, which is positive, so this is greater than 0. And now if we plug in a value of x that's between 1 and 2, let's just say 1.5, we get 1.5 minus 2 is negative, 1.5 minus 1 is positive, so we get a positive times a positive, which is negative, which means our derivative is less than 0 on this interval. And then the last interval that we want to look at is when x is greater than 2. So let's just plug in 3. We get 3 minus 2, which is positive, 3 minus 1, which is positive. So positive times a positive is positive. So our derivative is greater than 0 on this interval as well. And now we know where our function is increasing or decreasing. Wherever our derivative of our function is greater than 0, our function is increasing, and wherever the derivative of our function is less than 0, our function is decreasing. So we're increasing from negative infinity to 1, or when x is less than 1, and from 2 to infinity, or when x is greater than 2. And then we're decreasing in this interval from 1 to 2. So from 1 to 2 is where we are decreasing. And for part B, what we're going to find are the local maximum and minimum values. And the way that we do this is we have to find the zeros of our derivative, which we actually already found. We're at x is equal to 1 and 2 in part A. And then we're also going to use some information we found in part A as well to figure out if these are maximum or minimum values. So if we look at values of x that are less than 1, our derivative is positive. And then for values of x that are greater than 1 but less than 2, our derivative is negative. So we're going from an increasing slope to a decreasing slope, which means that at x is equal to 1, we have a local maximum. Whenever we have a 0 at a point and we go from increasing to decreasing, we have a maximum, if that 0 is a 0 of the derivative of our function f of x. So the local max is at x is equal to 1. And if we plug in 1 back into our function, we should get a value of 2. This is equal to 2. So we have a max at the point 1, 2. And now if we look at x is equal to 2, well, our derivative was negative for values less than 2 but greater than 1, and then our derivative was positive for values greater than 2. So we're going from decreasing to increasing slope, or from positive to negative values of our derivative, which means this is a local minimum. So local min is at x is equal to 2, and now we just plug back in 2 into our original equation, and we should see that this is equal to 1. So we have a local minimum at the point 2, 1. And now the last thing that we're going to have to do in part C is figure out the intervals in which our function is actually concave up or concave down, and also find the inflection points. So if we look back at the equation for our derivative, it was 6x squared minus 18x plus 12. So the derivative of that would be 12x, if I take this 2 down, minus 18. So the second derivative of our function, or f double prime of x, is equal to 12x minus 18. And so now what we want to do is set this equal to 0. So 12x minus 18 is equal to 0. So 18 is equal to 12x. And x is equal to 18 over 12 which is equal to 3 over 2. So we know that we have a 0, the second derivative of our function is equal to 0 at x is equal to 3 over 2, and now we just have to make sure that this is actually an inflection point. So what we want to do is look at values of x that are less than 3 over 2, and then look at values of x that are greater than 3 over 2, and see the sign of our second derivative. So if the sign of our second derivative is positive, that means that we're concave up, and if the sign of our second derivative is negative, that means we're concave down. So if we plug in a value of x that's less than 3 halves, let's just say 0, we get 0 minus 18, which is negative, so our second derivative is negative on that interval. And if we plug in a value that is greater than 3 over 2, let's just say 2, we get 24 minus 18, which is positive, so our second derivative is positive on this interval. So since we go from negative to positive, we're actually changing in concavity from concave down to concave up, which means that this is indeed an inflection point at x is equal to 3 halves. So what we can do to find the y-coordinate of this point is just plug this into our original equation again, and if you do all these calculations and plug this back in, you'll see that this is equal to 3 over 2. So we have an inflection point at 3 over 2, 3 over 2. And now for the intervals in which we're concave up and concave down, well, we're concave down whenever our second derivative is less than 0, so we're concave down for all x being less than 3 halves. So you can say concave down from negative infinity to 3 halves. And then we're concave up wherever our second derivative is positive, which is for all values of x that are greater than 3 halves. So concave up from 3 halves to infinity.